Welcome to our next lecture on architectures of artificial intelligence systems. Today we are going to talk about modularization and generally some fundamentals, basics of code engineering for data science, which are, I think, in my personal opinion, key skills of machine learning engineers. So the topic for today is clear, modular, and well-documented machine learning code. So when we look at the place of this module in our course, we are here in the core processes in modularization. So this is the key input for machine learning pipelines. As we mentioned previously, machine learning pipeline is just a sequence of components and artifacts. So we're going to talk about components nowadays, and will be later on utilized in specifically here in containerization, okay? Because knowing how to modularize the code will help us to design the architecture of containers. So let's start. For some of you, concepts covered in this part may be a bit trivial, but let's treat it as an intro just to organize and clarify key concepts in code engineering, specifically in the machine learning context. So, as I already mentioned, 95% of the time spent on machine learning projects is spent on things other than modeling. So machine learning code is just 5% of the total time spent. In many cases, many projects. Some other aspects cover things like configuration, automation, data verification, data collection, feature engineering, testing, debugging, resource management, model analysis, process management, etc., etc. And first fact we should be aware of in the context of such processes is that each machine learning stage may be in the independent system. So we may have a separate system for data ingestions, like here, pointed here as a system 1. A next dedicated different system just for data prep, model training, model evaluation, model validation, okay? And the next one for serving the model to the customers and monitoring its performance, not only performance of the model, but also the performance of the infrastructure. So each machine learning stage may be an independent system, and that's why we need so-called composability. That is one of the key features of our architecture. Composability is the ability to compose a bunch of microservices together, and the option to use what makes sense for your problem. So that was the first observation, motivation for composability. Next fact, each stage in this typical machine learning project has its own goals and specifics. We have already covered this in our previous lecture. So we have the stage of experimentation stage, development stage, maintenance stage, and is managed by different teams. I have already mentioned about the machine learning DevOps. We're going to cover this later on. DevOps, we already mentioned that this is the methodology where developers work closely with operations to maintain and develop the code. In machine learning, we have something new from the qualitative point of view, because just a rough intuition for you. Usually when you modify the code, the request for modification comes from the final user. Then developers make analysis and modify the code by themselves. In machine learning world, it's a bit different. Firstly, the need for the modification of the code, if you treat a machine learning model as a code, comes not from the humans, but from the reality. Our systems identify some model drift. They identify that after some time model quality decreases model decays. So this is the automatic signal coming from our monitoring systems, not from humans. Secondly, it is not modified by hand by developers, by automatically by the training pipeline. So as you can see, here you have data, which is a trigger for modification, and the model, not a code, but the model which is modified. So these two qualitative changes made developers and project managers to think about a kind of new methodology which combines DevOps with machine learning world, and that's why we have ML DevOps. But from our perspective now, is that all those stages are managed by different teams which may use different methods, different tools, they have different habits and different cultures. So for example, data scientists prefer to write their code in interactive mode, Jupyter Notebook, most cases, yes, even if it's a Python code, it's still interactive. Developers prefer IDEs like Microsoft Visual Studio Code or PyCharm. So they do not write interactive code, they write the whole scripts, yes, as files. Operators, or if you operationalize the model, in many cases work with just command line interfaces, yes, so they do everything with scripts, not the code, just not to touch the code itself. So as I said, different methods, different tools, different habits, different cultures. So when you look at this, we have different systems and different teams in the experimentation stage, different systems, different teams in the training stage, different systems in the deployment stage, for example, in the cloud computing. So for that, we need so-called portability. This is the next feature of our architecture, of our system. Portability is the ability to efficiently transfer key microservices between different environments. So, and the third observation, eventually, you will grow up. Okay, after some time, you will need more resources, you will have more customers to serve, so that's why you need so-called scalability. Next, very important feature of your system architecture. So maybe after some time you will need some more accelerators like GPUs, TPUs, whatever. More CPUs, just the computing power, or maybe more disk space, yes, maybe more networking for transfer. On the other hand, it's not only about the infrastructure. Sometimes you may need more skills on board, data engineers as a key role, data scientists, etc., or more teams. So just to prepare for that, you need to make your architecture scalable from the very beginning. More experiments. So your machine learning framework has to support composability, portability, and scalability. A machine learning framework you choose for development as a part of a technology stack, but also the architecture you design. So let's start with clean, modular, and documented code, some basic information about that. Clean, modular, and documented code, just a very, very brief introduction to code engineering good practices for machine learning developers. So let's start with clean code. Just few tips, simple tips. It's like in primary school. Firstly, use meaningful names. Be descriptive and imply type. For booleans, you can prefix it with is or has underscore to make it clear it is a condition. You can also use parts of speech to imply types, like using verbs for functions and nouns for variables. Avoid abbreviations and single letters. This is very typical for beginners, okay? Your goal is the code that one can determine what makes this expression based on the audience for your code. So if you work with other data scientists, certain variables may be common knowledge, like if you import pandas data frame, you always write df, yes, so this is a kind of the consensus. But if you work with full stack engineers, it might be necessary to provide more descriptive names in these cases as well. Use meaningful names. Long names aren't the same as descriptive names, so good function names describe what they do well without including details about implementation of highly specific use cases. So for example, here as you can see, you may imagine a very long name, like counting values of names list with sets. Okay, it's not too good, it has too many descriptive statements. It's better to say count unique values, for example. Yeah. Just to check whether your code uses meaningful names, you can ask a fellow programmer to guess the purpose of a function or variable based on its name without looking at your code. That's a good test. Maybe, I hope it's gonna be a habit in writing the code. We'll see. Next, use white spaces properly. So this is the next rule I encourage you to use in code engineering and clean code good practices. Use constant indentation. Separate sections with blank lines. Limit your lines to 79 characters. You can use PEP 8 Python rules, yes, requirements, standards. My checklist is typical. This is an example of my personal checklist. So my variables has meaningful names. For booleans I use meaningful prefixes. Has, is, I avoid single letters as names. I use white spaces properly, so I use constant indentation. Sections are separated with blank lines. Lines are limited to 79 characters, so that summarizes all the previous recommendations. So that's for clean code. And now let's go to modular code. So this is the typical data science code. We call it wall of text. That's what you may expect from a data scientist as the outcome. Those people who focus mostly on testing and experimentation are not focusing their work on the clean code. As you can see, you'll find a lot of very unintuitive statements here. To understand this, it's extremely difficult. Such a code may run perfectly, but if we don't understand how and why, we can't do anything with that. And this is a very interesting quote, my favorite, from Martin Fowler, quite old one. And a fool can write code that a computer can understand. Good programmers write code that humans can understand. So sometimes we need to translate WOT, wall of text, into something understandable to programmers. So how to do this? Firstly, logically broke up into functions and modules. Okay, so we may broke the code into functions with some different definitions, with different names, and if we need some higher level structure, into modules which are later on imported from our drive or sometimes installed in the cloud, then others can install it with pip install, for example. Such a code is more organized, efficient, and reusable. Some cases, module is a file. Modules allow code to be reused by encapsulating them into files that can be imported into other files. Obviously, we need to find a kind of the balance, because we won't always write modules for example, only 5 functions. But if you exceed the 10 functions, for example, then it's good to think about small modules. And now, this is interesting summary I have found somewhere in the net, a kind of the quality check in different dimensions. And the first question you should ask yourself, how code is structured. So bad thing is that the code is monolithic, complex, large functions and mod methods. Good code is modularized. Functionalities are logically grouped into smaller functions or methods. So that may be a kind of the checklist. On the left is bad, on the right is good. Next, how code is written. Confusing variable names, commented out code, dead code. Good practice, strong encapsulation, naming conventions, easy to understand for humans, function, module, and classes, docstrings, descriptions. I'm going to speak about this later in a second. How efficiently it runs. Serial code on single machine with high complexity versus asynchronous calls. Asynchronous calls, a very, very important concept. Distributed and as low as possible complexity. Make it easy. How easy it is to troubleshoot. Nested logic code varies in for or while loops, no logical boundaries, versus decoupled functionality allows for testing per logical groups. And how much information is retained about each run? Print statements only, little or no metrics or stats recorded, no artifact storage. Retention of logs for each run, metrics and artifact storage. We're going to cover this in experiment tracking section of this course. So as you can see, this is a quite nice checklist. Go from left to right, ask yourself whether your code passes this test, and continue. And next very good practice is dry. You have probably heard about this. Don't repeat yourself. Modularization allows you to reuse parts of your code, generalize and consolidate repeated code in functions or loops. Bad example, just have a look at this. And just a bit better. And really better. Okay. So as you can see, it's also good practice to abstract out logic to improve readability. Abstracting out code into a function make it less repetitive and improves readability with descriptive function names. So abstracting out the code into function, that's a good idea. But on the other hand, use your judgment. It's possible to over-engineer this and have way too many modules, so do not exaggerate your writing the function for everything, okay? We need to find a kind of the balance, okay? Just for dry, don't repeat yourself rule. Next tip, minimize the number of entities, functions, classes, modules, etc. Creating more modules doesn't necessarily result in effective modularization, so you have broken up your code in an unnecessary amount of functions and modules. You'll have to jump around everywhere if you want to view the implementation details for something that may be too small to be worth it. So don't exaggerate. General idea, rule of thumb is functions should do one thing. One function, one thing. So generally, if there is an and in your function name, consider refactoring. Okay, so that may be a rule of thumb for scope of the function. And that's another rule, fewer than 3 arguments per function. Okay, so this is not a hard rule, obviously, and there are times when it's more appropriate to use many patterns, but in many cases it's more effective to use fewer arguments. It's just for better understanding of the code, easier debugging, etc. So my checklist, just to sum up this set of rules, kind of the summary as I did previously. I don't repeat any part of the code within my program. The number of modules and functions is reasonable. This function does only one thing. This function has not more than 3 arguments. That may be also a checklist for you. Okay, so now let's go for documentation. What does it mean, well-documented code? We have many different types of documentation. One of the most popular is are inline commands. So you may use it to explain parts of your code, document its major steps, describe history, motivation, limitations. For example, I didn't know how to do this, so I did it that way, but it should be developed. And to-dos, yes, so you probably know that to-do statement is also managed by IDEs like Microsoft Visual Studio Code for task management system, so you can create your task from to-do lists. Okay, so these are inline commands. You have a bit more advanced docstrings. So as you can see, you may have a module docstring at the very top or a function docstring. So the explained functionality of any functional module in your code are surrounded by triple quotes. So it's something more than just one line comment. So I have one line docstring like this one. So as you can see, just a very short description of what the function does. Or multi-line docstring, and this is my favorite favorite shape, because I do not only write what does the function do, but describe the inputs and outputs on the function, including the variable type and the meaning. Okay, so that's in my personal opinion good practice. By the way, just remark, if you are using, for example, generative AI to support your coding, like I do with GitHub Copilot or some other tools, you may reverse the engineering process. So we may start with such descriptions and then ask the system to generate the code for you, obviously taking very carefully and checking very carefully the results, because they may be sometimes wrong. And as you can see, it's not like that you start with writing the code and finally you end up with, at the very end of the writing the function, testing, you make the description. I suggest to start working in an opposite way, start with the very specific documentation of the code, your needs analysis, and basing on that description, you can generate the code itself, just to consider. Good practice also, in Python we have PEP257 docstring conversion. It's, by the way, hyperlinked in my PowerPoint, so if you just simply use that and click, you'll be redirected there. So that's for inline code. And the next stage is a project documentation. So this is typical README file you store on GitHub. In project documentation, you should follow also very specific guidelines. You should write why and how the code is relevant to the user, what it does, what are the dependencies, requirements, and how to use it. Okay, these are the key points of this README. Seems trivial, but it is not. And once upon a time, I took this course from Udacity. It's also hyperlinked here. How to write READMEs is free course. I strongly recommend you to go through this course, to take it. Yeah, as you can see, very nice mission, because code is for humans too. Yeah, so follow this course on how to write good README MD, and I hope it will stay with you forever and make your life and your peers' life easier. Not only your peers' life easier, but also your life easier, because if you would like to come back to your code after a few years, you'll know how it works. So write README files just for your future self. And this is my message to you. I always keep it in mind that way. So some useful tools for that. Let's have a look. Firstly, PyLint, a very interesting library, Python library. It's also hyperlinked here. Nope, it's not hyperlinked, but you can go to the internet, you can pip install it, and it will check the compliance of your code with PEP 8 requirements. So if you look how it works in practice, so this is the bad code. If I write plint, as you can see, mod underscore bad dot py, it will generate the feedback, and it will score in the range from 0 to 10 the quality of my code, and generate some suggestions. As you can see, it has been rated 5.71 in the 10-point scale. Okay, so you can scale it, and then later you have AutoPep, a library which attempts to automatically clean up your code. So you can use this to clean up your code. So for example, before my code looked like that, And then when I write autopep with those parameters, aggressive parameter, myscript.py, it will generate quite clean code. Okay, you may ask yourself, okay, we can do the same with, for example, ChatGPT at the moment, or for example, GitHub Copilot. Yes, you do, but beware, and this is my practice, that for a bit more advanced code, ChatGPT generates a lot of errors. So the code compiles but does not the job correctly as I wanted. And those iterations sometimes are very painful. Obviously, it improves from the version to version, but it still needs an attention. And secondly, you can use this autopep tool or this PyLint tool during your CI/CD pipeline. So, for example, in the continuous integration, when you perform the test of the code, you can make it automatic. So those libraries, to the best of my knowledge, do not apply generative technologies, which sometimes are unstable. But obviously that's another window at the moment that we might think about such automatic testing using better and better generative tech. That may be, by the way, quite interesting idea for a project. Not for this course, but for the future project. Okay, so we have two tools. First one checks the compatibility, quality of the code. Second attempts to improve it. And now let's go to some examples of the methods covered in this quite long lecture. All those examples are included in the folder of this course. So the first one is just a simple regression, and this is a very toy training of the linear regression model. And just to show you different options of modularization, I have put this into that different files. I started with a whole code, but later then I split this into different separate files with separate folders. So this is the example of modularization. And how to approach this? This is my typical workflow. I start with my checklist. So I tell myself, okay, this is so-called precise product breakdown structure. So we call it code breakdown structure. I do it, as you can see, in a notepad. So the script, precisely speaking, this is a markdown file, but never mind, it's text file. The script will perform the following task: loads the data, trains the model, evaluates the model. Okay, so then when I write my code, I just simply click those checkboxes, but it automatically generates also the structure of the code. So as I previously mentioned, pipeline is a sequence of more or less advanced sequence, because we may have obviously different decision trees in our code, but let's keep it as a sequence for simplicity at the moment. Components and artifacts. So such a checklist serves as a basis for this decomposition, okay, using artifacts, components, and decisions. Yeah. So after the decomposition, my checklist looks like that. So I say, okay, for this project, I will have the following artifacts like inputs and outputs, like initial training file, and I put the name here. This is still the data needs analysis stage. So I do my best to write down those names during needs analysis, just not to think during the coding stage. Generally, that's another approach I use after many years of programming, that I try to separate planning from doing. Yes, obviously also need to find kind of the balance, because it's impossible, close to impossible, to plan everything from scratch. We need sprints. But for a given sprint, I do such a planning, and then I go for coding. And believe me or not, it's really good to do something like this with pen and paper without any computer. Next, components which do things. So I need a component which reads the data. So for me, this is one.readPy. Apologies for this typo. Training 2.trainPy. So I have some input, actions, and output. As you can see, this is becoming typical for the pipeline. So I specify what's the input. Next, what the component does and what's the output. Training, the same. Evaluation, the same. We may also write something like that in a spreadsheet, Google spreadsheet, whatever spreadsheet you like. That's another, I use that for some time, but at the moment I use some different tools for that. So I write my artifacts, components. As you can see, it generates quite nice flow because I have a name of the file, I have some input, I have some output with the names and specification of the functions. If I keep this, that's also quite nice technique. Or if you would like to go a bit more advanced, you can use Joe.io to visualize such a pipeline. And Joe.io, you can generate the quite nice graphs, yes, so you can hide them, you can generate the graphs which are diagrams which are at different levels of complexity. You can add different metadata to such objects, etc. So the result may be like this one. So next example I have provided you with in my course materials are customer analytics example. And for that, I took this Medium post, Medium, because medium.com is on top of towards data science, very powerful source of knowledge in data science, in my personal opinion. This article is very, very good because it shows you many different examples of different data science project for e-commerce. So I took only one part of this for customer segmentation, and that was my real checklist I did some time ago without generative AI, completely without any support from ChatGPT or GitHub Copilot. So it took me 9 minutes to organize the code. If you click this, you will see how it's organized, yes, because it's quite wall of text code. So I set up the folder, get the data. Next, I spent 2 hours to create my own Jupyter notebook, 25 minutes on EDA, exploratory data analysis, 30 minutes on clustering, 60 minutes on customer lifetime value prediction, yes. And then I did the refactoring of the code, which took me around 3 hours from Jupyter to Python, yes. So that was the time. At the moment, obviously it's gonna change because we have much better tools to support our activities, but still it was the real activity. Next example you have is the example from Dataiku platform. I took this example on high revenue customer classification and wrote it in as a Python code, and we are going to use this later on for MLOps. So if you probably remember, this use case looks like that. So we have some customer data, order data, I perform some cleaning, prepare the orders data. We group by those by the customer and merge this with the customer's data. Next, we perform some cleaning once again and get the training data set. And on that, we train the model, and finally we evaluate the model, or not evaluate, we just simply apply this model to unlabeled customers. So this is also the example. You have this code refactored to Python in my script. And the final one is quite a large project for tweet classifiers and disaster response, where we use natural language processing models to classify the content of tweets, SMSs. That was done before generative AI. So I used just traditional good old-fashioned NLP models for that. So as input I had a tweet, then I trained a model which was capable to classify the tweet to different types of threats in order to later on pass it to different teams, emergency teams. So as you can see, I did this from the very beginning, then I identified created different functions to modularize the code, and then finally I put those into the dedicated folders. So this example is also for you just to have a look. So that's all for this course. As I mentioned, that forms the basis for your good code engineering practices, and I hope it will be helpful for you in your future career and specifically in this course later on. Thanks a lot. Happy coding. Thank you.